Hello, this is Sets Sheet 6 and we're going to learn about push forward and pull back of sets along maps. And so this is really, we're just learning a little bit about the API for sets here. What am I talking about? The idea is, let me go through the maths. We've got a function from x to y. And then given a subset of x, we can push it forward and get a subset of y, right? And mathematically, we often write this. We often write f of s. You may have seen this before. If little x is in capital X, then you can write f of little x, and that's in capital Y. But if s is a subset of x, then sometimes people write f of s to be the corresponding subset of y. You just take all the elements of z, you apply f to all of them, and then you get a subset of y. So the subset of y is this: it's the y such that there exists an element of x with x in s, and f of x is y. And the notation doesn't work. That's one of the things I wanted to. You can't do f of capital S. If you tried f of capital S, Lean would say f is expecting an element, a term of type x, and you've given me a term of type set x, so I don't get it. And so we have this slightly weirder notation here, f prime prime s. And similarly for pullback, the inverse, that inverse notation is reserved for inverses in things like groups. And so we have a modified inverse primed notation for the pre-image of a subset of y. So let's go. What does this first lemma say? Oh, there's only 4 goals in this. Great. There should be a short video. There's 4 sorries. The first one says that if S is a subset of X, and then you push it forward to Y, and then you pull it back to X again, then you end up with something that's bigger than the thing we started with, or at least as big. So let's just do intros X, H, X to see where we are. So little x is an arbitrary element of capital X, and the hypothesis is that it's in S. And now the question is, why is X in the pullback of the push forward of S? And the definition of this thing here, the definition of X is in the pre-image of F inverse S. We could change this to F of X is in something, right? Yeah. So that's the definition. And now what's the definition of F of X is in something? So we could change that to be, that there exists some X, exists some Y such that something. Yeah, maybe I'll call it X primed. I probably could have done that straight away, yeah. And do you see, when you're using change, you don't have to write everything out in full. You can just get away with, you just give Lean a clue. It's like, I want the exists form. So we've got an element of X, and we've got a proof that it's in S, and we now have to prove that there exists an element of X which is in S, and that satisfies f of it is f of X. So I hope you can see that letting X primed be X is probably a good idea here, because X is in S, we know that, and f of X equals f of X is true by REFL. So we could do use X and then split, and then this is exact HX, and then this is REFL. So there's a proof, but somehow, instead of the split, we could just do instead of the split, we could just do this, right? There. And then in fact, instead of the use, I think we could throw the use in. Can we do that? There we go. And then we don't need the change. And so there's the proof. Use X, whatever, etc., etc. Also works. So that's interesting, and one wonders whether we could do the same sort of thing here. Well, so now what are we're trying to prove that if we have a subset T of Y, then if we pull it back and then push it forward, we get something that's contained in T. So I guess intros Y, HY. And now, that says Y is in the image of something. And so actually HY says we could change that there exists some. Can we do this? Exists something, comma something at hy. Will it like? Yeah. So you can see that hy is actually an existence statement. So we could do cases on it, right? We could do cases hy, and then we get some stuff. But intros and we don't need the change, and the intros and cases we could do with rintros. So this could be xhx. And the hx is an and. So this could be hx1 and hx. We could do hx1 and hx2. But hx2 says f of x equals y, and y is an arbitrary element of capital Y. So we can do the Ruffle trick for this. We could do Ruffle. And now there's no y's at all, so now we didn't even need to name y. And now hx1 may as well just be called hx. So what have we got now? Now x is in f inverse of t. That means f of x is in t. I think that this is exact hx. Yeah, it is. So there's a rather slick proof of that. So, and then this one here. Yeah. This is that they form a Galois connection. So this is if you know anything about category theory, then what we're saying is that the pullback functor and the push forward functor are adjoint functors, is what we're saying. If you don't know anything about category theory, but you know something about order theory, then we're saying that pullback and push forward form a Galois connection. You see one of those in Galois theory. You've got an extension, a sort of a finite Galois extension L over K, and then you have subgroups of the Galois group, and you have sub extensions of the extension, and there's ways of moving from one to the other in both directions. Given the sub extension, you could look at the elements of the group that fix that sub extension, or given the subgroup, you could look at the things fixed by all the elements of the subgroup, and they satisfy an analogous assertion of this nature. Although I suspect that one of the inclusions might be the other way around. I think it's contravariant, the Galois theory one. So these are called a Galois connection in honour of Galois. And right, let's. I mean, that doesn't help to prove it. Let's prove it. Is it Ruffle? Okay, so I think we've got to do split then. I'll tell you what we could. I mean, we might be able to do simp. Yeah. It's the simplifier knows it. And if we do squeeze simp, it'll tell us what it's called. It's called set image subset if. Let's have a look. Let's have a look at the proof of set.image subset if. It's called ball image if. That ball doesn't mean balls in metric spaces. That means bounded all, I suspect. Let's look at the proof of that. It's just by simp, so that's no help. We never got to the bottom of it. Okay. There's only four goals, so I may as well prove it. So split. I quite like doing these proofs, and now sorry, I need to change it to two sorries. I just used my snippet there. I hope you like that. Intro H, and now what? Intros H, and we've got to prove an inclusion, so probably X will be, and then HXS, and now we've got to prove that X is in that. So we've got to prove that f of X is in T. So we could probably apply H. Does that work? Yeah. In fact, let me go with refine H underscore. And now I've got to prove that f of X is in f double primed of S. So that goal is an exists. I've got to prove that there exists something in S such that f of it is f of X, and the answer is H. It's X. So, and now, so that instead of that this is what refined. Refined is like exact, but with holes. So now that hole there, I need to prove X is in X. Sorry, X is in S, and f of X is f of X. So HXS will do for that, and now I've got to prove f of X is f of X, and that the proof of that is Ruffle. There. I mean, at this point I'm in term mode. I'm writing terms, and so Ruffle without the E is the term, and Ruffle with the E is the tactic. And you know, if they'd just called them the same thing, then a whole lot of people wouldn't be asking what the difference was between ruffle and raffle. So I think they missed a trick. And now let's see if we can do this one in 2 lines as well. So this is rintro. Let's go with rintro x, no, hx. And now this says this is the exists. Oh, that should be y. Oh, I've done this one. There's a, where is it? It's this here. I think it's this. I think I've just got to do that. I think that was the same. Yeah, that's worked at least. Oh, do you know there's a you can do rintro question mark, I think. Ha, that didn't help at all. Let's go back. You can do rintro question mark, but it doesn't work on this occasion. Let me do. No, let's press on. And now this is probably the f of x is in t. That says x is in f inverse of t, so I might be able to reply h again. Let's refine h underscore. That's what there we go, hx. So that's the proof of that one. So if you're interested, oh, so there you go, I even mention it. This proves that the function which is pushing forward and the function which is pulling back form a Galois connection. And if you work out, I mean, we could unfold Galois connection to see what that means. And so then we get intros S and T. And you can see that it's the same goal. Well, they use less than or equals to because they're treating everything as a partial order. So in fact, if we change this example, why did that happen? If we change this example to, if we give the theorem a name, we could call it Galois connection GC. Then this would be this is probably just apply GC. Yeah, there we go. So that's the proof that it's a Galois connection. Yeah, okay, that'll do. Could I've done it there? Yeah, I could have done. So, and I probably could have done it there. Oh yeah, look at that. So, I mean, maybe I'll stop messing around. I guess that's the end of this video. Thank you very much for watching.